Hi everyone, it's Mr. H here. In today's video we're going to be looking at applications of magnetic fields and charged particles. What you see in front of you is a picture of a mass spectrometer. What happens is electrons fire out of this electron gun and then they go through what's known as a velocity selector, and we're going to talk about how that works. And then eventually they enter into this part where there's a magnetic field coming out of the page, and depending on how big they are, they actually bend at different radii. We're going to look at how that works as well. There's one piece that's not shown in this. Oftentimes you have right here, after coming out of the electron gun, there's also a particle accelerator that just speeds those up to a certain speed. That might actually be built into the electron gun itself as well. And so all three of those pieces together form a mass spectrometer. We're going to break that down, look at each one, and then add them up and look at a full mass spectrometer at the end. So the first thing I want to point out is that if we have a magnetic field that's perpendicular to the direction of a charged particle, then we get circular motion. So let's see what this actually looks like. The path of a charged particle in a magnetic field is circular. So if I was to draw just this two-dimensional shape, and I'm going to have a magnetic field that's going into the page across this entire sheet. And what I'm going to do is I'm going to bring a charged particle, let's say it's a positively charged particle, we're going to bring it into this magnetic field. And so we know that if the speed and the magnetic field are perpendicular to one another, then the force is perpendicular to those. And so based on the right-hand rule number one, our thumb is in the direction of the charged particle's velocity, our fingers in the direction of the magnetic field, and our palm points in the direction of the force. So as this comes into this magnetic field, it's going to experience a force in this direction. And so that's going to cause it to start bending. As it begins to bend, now its velocity is in this direction, and the force is going to be perpendicular to that. And then as it continues to bend, it's going to continue to feel a force that's perpendicular to its direction of motion. And it's going to ultimately cause it to travel in circular motion, just as shown there. And so that's what's going to happen. And so we can do some math on that. Because the magnetic force is always perpendicular to speed, we can say that the magnitude of that magnetic force is equal to the magnitude of the centripetal force. We know that the centripetal force from previous physics is mv squared over r. And we know that the magnetic field is qvb. And the reason we know that the force of the magnetic field is that is because we know that the speed and the magnetic field are 90 degrees to each other. So sine of theta becomes 1, sine of 90 is 1, and so it's just qvb. And so rearranging that for r, we can actually figure out what the radius of curvature is actually going to be. So if I multiply both sides by r, I get r up here, and then I divide both sides by qvb, I get this divided by qvb. I cancel out the v's, and I could figure out the radius of curvature if I knew the mass, the speed at which the particle was traveling, the charge on the particle, and the magnetic field. And that's one of the things you'll be calculating in today's homework. So that's a really useful formula to allow us to figure out the radius. And we could rearrange that and solve for other things too. We could figure out what the charge on a particle is. If we knew the four other variables, we could figure out the speed, the mass, we could figure out the magnetic field. So if we know any of those four variables, we can solve for a fifth. So that's basically how we get the circular motion in a magnetic field. And that's the end part of this mass spectrometer, the part that we see right here as it's curving. In this case, we see the magnetic field coming out of the page. Let's look at a second thing, and that is how particle accelerators work. So it's the part I talked about here that's not shown in this diagram, but actually getting the particles up to speed. How does that work? Particle accelerators work like this. They have a particle source, so the particles need to come from somewhere, and they need to have accelerating plates, and they need to have a series of magnetic fields to direct the plates. So in this case, I could draw a simple particle accelerator like this. So I have one plate on the left, another plate on the right, and what I'm going to do is I'm going to have a charge flowing between those, or I'm going to have a current flowing between those to charge those plates rather. And so if I can have some type of radioactive source, it doesn't have to be radioactive, but often it is, what's going to happen is that's going to release some charged particle. Could be something positively charged like an alpha particle, it could be something else. And then we're going to have right over here, we're just going to have a small hole. right here. And we're going to send those straight out towards the hole. These are, as soon as it passes through the hole, what's going to happen is there's going to be some charged plates here. And so these magnetic fields, there's going to be a magnetic field out here that is directing the particles. And that's going to help it go between the charged plates. And so we have these particles being sent, and we've got an electric field that's traveling in this direction. And so the particles, if they're positively charged, are going to travel across like that. They're going to go through the hole. And we could do some math around kinetic energy here. We can say the kinetic energy gained is equal to the electrical energy that is lost by those particles. And so talk about 1/2 mv squared, that's equal to the electrical energy is Q times the electric potential difference. And so they move out of that electric field, losing that electrical energy, but they're gaining that kinetic energy. And that's the basis of that. Now we often measure energy in joules, but in this case the energy that particles have is measured usually in electron volts. 1 electron volt is equal to 1.602 times 10 to the negative 19 joules. Well, you might think, I've seen that number before. In fact, that's the number of, or that's the charge in coulombs on an electron. Well, this is equal to the energy, this energy is equal to the work done on an electron in accelerating it through a potential difference of 1 volt. So if you consider this, we're going to take that, going back up to this equation right here, we're going to take that charge of 1.602 times 10 to the negative 19 coulombs, and we're going to multiply that by 1 volt. And so coulomb times volts gives us units of joules, and then we're just saying here that we're just finding this new thing as 1 electron volts. So that's what we measure things in. In the case of the CERN Large Hadron Collider over in Switzerland, what you'll find is they're measuring particles at 14 tera electron volts. So these are particles that have tons of electrical energy that's being converted to kinetic energy. They're traveling incredibly fast. It seems like a small number that they would only have for a single particle, 2.243 times 10 to the negative 6 joules, which is tons of energy for a single particle. I don't know of anywhere else on Earth that we've been able to get particles moving this fast. It's remarkable that what they've been able to do, and billions of dollars from governments and science agencies worldwide have been invested into the Large Hadron Collider in Switzerland. Large Hadron Collider is fantastic and amazing, but I want to talk about something that we've seen in TVs up till about 2000, 2010 that was a simpler mode of how a particle accelerator actually worked. And that was when we had these cathode ray tube TVs. And so what we had is we had these curved screens, and the reason we had these curved screens is because what was happening is electrons were actually being fired from the back of the TV and being bent by magnetic fields and bombarded onto the screen. And that's why when you touch the screen, you'd get an electrical shock of some sort. You'd see some static buildup. And so you have all these pixels on the screen that are getting hit by electrons, and based on what pixel gets hit, it's going to light up that pixel. And so if you pull apart a cathode ray tube TV, what you see is something that looks like this. You have, in this cathode ray tube TV, you have the particle accelerator right here. And so that's in a tube, but it's doing the same thing that we just described. We've got the particle accelerator, and then you have a plate on the top here and on the bottom, and a plate on the far side on the closest side to us. And what those plates are doing is they're going to become charged, and the charge on those plates is going to change very, very rapidly. And as that changes very rapidly, it's going to send one particle bending, and one particle might fly off to this side. It's going to send another particle bending to the next one below it, another particle bending to the next one below it. And so in a matter of 24 times every second, they would send enough electrons to light up all the pixels on the screen. So you can just imagine how fast those charges are actually having to change on the plates. All the circuitry and wiring that you see here is what's determining how to change those charges so that those electrons get bombarded properly onto the screen. And so occasionally you'll see a TV like this that will have one line that doesn't seem that it's showing up, and that's because what's happened is it's not calibrated properly anymore, that somehow the electrons are not hitting the pixels in that line on the screen. So the third application I want to investigate is the velocity selector. It's used to make sure only the particles with the correct velocity get through. The velocity selector consists of cross-magnetic and electric fields so that the forces, and we're talking specifically here about the force due to the charge, so the electric force, and the magnetic force, are balanced only for particles with the correct velocity. Now, I haven't accounted for gravity, but gravity would also be something that would play in here. But if you consider just how fast many of these particles are traveling through a velocity selector, they're traveling so fast that the force of gravity is such a minuscule difference compared to the other two forces that are acting on it. So we're not accounting for the force of gravity. So this is what a velocity selector actually looks like in a practical sense here. We have a charged particle coming into two plates. So I've got a plate at the top and a plate at the bottom, and this is going to be connected to a circuit, and that circuit is going to charge the top with a positive charge, and it's going to charge the bottom with a negative charge. And we then run a magnetic field that's traveling perpendicular to that electric field. So we got the electric field traveling this way, we've got the magnetic field traveling into the page in this case. And what that means is as this particle moves into these fields, it's going to experience, from the right-hand rule, it's going to be traveling in this direction, so its velocity is that direction, so its force based on the magnetic field is going to be upwards. Fingers into the page, thumb in the direction of the velocity, palm opens up. So the magnetic force is going to be this way, and then we're going to also have a force due to the electric field that's downwards. And so assuming that that is moving at the speed we want, the particles that we want are going to come out smack in the middle, right where we want them. The particles that we don't want, so this is the wanted speed, the particles we don't want, if they're moving too slowly, are going to be affected more by the electric field. So these ones are going too slow. And the ones that are moving too fast are going to be affected more by the magnetic field, and they're going to be pulled off to the side as well. So what exits from these two plates are exactly the ones we want, and they're going to be traveling through. Everything else is pulled off to the side and hits one of the plates. And so we've selected exactly the particle speed that we want. And as I mentioned earlier about the CERN Large Hadron Collider, they're using that to get the speed particles that they want initially. They're making sure they have exactly calibrated so that they're using the speed of particles that they need. Mathematically speaking here, we can see that the magnetic field is, the force of the magnetic field is equal to the force of the electric field for the particles that it selects. And so because, again, we have the speed perpendicular to the magnetic field, sine theta is 1, so it's just QVB. And we have Q times the electric field intensity. And then we can go ahead and cancel out Q, and the speed of those particles is simply the electric field intensity divided by the magnetic field. And that's how we can calculate the speed using a velocity selector. So putting all these together, we get a mass spectrometer. A mass spectrometer is an apparatus used to find the mass of elementary particles by moving them through a magnetic field and determining the radius of its path. So we have the particle accelerator, that then the particle moves through a velocity selector, and then once it moves through the velocity selector, it's going to go into this area where there's a magnetic field that's going to be exerted. We use the right-hand rule to determine that, as described in the first part, and we can see that it's going to move in this circular motion. The heavier particle is going to have a wider radius and is going to strike the screen further out. So as we said earlier, the centripetal force, because this is moving in a circular motion, is equal to the magnetic force in terms of their magnitudes. And centripetal force was mv squared over r, and Fb is qvb because the speed and the magnetic field are perpendicular to each other, so sine theta is 1. Then we just go ahead and we rearrange this for the mass, and we get qvb times the radius divided by the speed squared. Cancel that out, we get qbr over v. So that's the math of how that works, and that allows us to figure out the mass of a particle. Check out the link below for some more applications of spectrometers.